Hello everybody. Wanted to do a quick walkthrough of the STAR-CCM user interface for all of you prospective 90-day to CFD training members. Make you feel a little bit more at ease with the software and how you can use it and what the user experience is like. So here's the graphical user interface, and pretty typical of CAE software. Main menu bars across the top, kind of this tree to the workflow, and down in the bottom left you have some more details about anything that you're selecting in the tree, and then you have the big window that you'll use for visualizing and interacting with your model. The first step in any good CFD process is the 3D Model Cad Generation or import. There are some CAD geometry tools in STAR-CCM that we could create our own geometry. Some of our customers, especially those who don't have a 3D modeling software like SolidWorks or Autodesk Inventor, they go this route. But myself, I prefer to make all of my 3D models in SolidWorks, and a lot of times that's what we're getting from our customers, so it just makes sense for us to go that way. So I'm usually importing a step file or an IGES, any of the solid part types. You can also import surface files, STLs, although sometimes the STLs can be a little funky and come in with errors. You can also use the native files. You do have to buy an add-on to STAR-CCM to pay those software vendors a licensing fee, but it's not much. And that way you even keep interactivity between that native file in Inventor or SolidWorks or Creo or whatever, where you can change a parameter in STAR-CCM and then have that parameter drive a change in the CAD model and go back and forth like that. Okay, but today's demonstration, we're going to go simple. We're going to import a surface geometry file. And let me pick an XT file that I have ready to go. So today I'm going to be demonstrating on setting up a model of ventilation in a room. So there's going to be a filter in the middle of the room, and we are going to try to filter out any kind of pollutants in the room. Specifically, I'm using this to demonstrate the particular best location for this kind of homemade DIY air filter room purifier made out of 4 furnace filters that you can get in any Home Depot store and a box fan that sits on top and the air blows out. Really cheap, really effective because it pushes a lot of CFM through the room, captures a lot of air and filters it, and it's really cheap, about $80 a piece. We are we built like 50 of these things for my kids' school, so we needed to know what's the best location in the room for them. So there's the CAD model. The first thing that we're going to do is call out the particular boundaries that are going to be our boundary conditions for the model. When you import, everything comes in as a surface. Everything is automatically going to be assumed to be a wall, but we're going to want to change that because we got to force the flow through this filter box. So I might want to take particular stats on the walls and ceilings, and so it would be useful to go ahead and get ready for that at this point by breaking out those boundaries. Call it wall, ceiling. And now we see the remaining surfaces. We're going to leave the floor and all the chairs and desks alone, and we're going to call out these 4 sides of this box as filters, which will eventually be our return outlets. And the last thing is the top boundary on that cube, which is the outlet of the box fan, which will be an inlet to our model. So that's all we have to do there. Next step is to set up some continua as we move down that part tree. We're going to set up some physics, and we have pretty simple physics today. It's three-dimensional, of course, but it is only gas. We don't need to do any of the multi-phase or other types of continua. And we're going to assume that everything's isothermal, and we can safely assume constant density. Segregated flow solvers, good for this kind of application. And we're going to run steady state. And let's make it turbulent and use K epsilon turbulence model. All this other stuff is just bonus multi-physics stuff that I would use in more complicated situations. Actually, let me take back one of those assumptions. Let's, instead of using steady state, let's use an unsteady simulation where we'll be simulating in time. All right, so the next thing we want to do is we want to move this part down to this folder here called regions. Regions are where you're actually going to have CFD type boundary conditions. You're going to have a CFD type mesh. The part, on the other hand, is just the CAD. And we do this because SimCenter STAR-CCM allows us to use parts-based operation definitions. So if later my CAD model changes, I simply replace the CAD model at the part level. All the operations are predefined to be performed on that part. And so therefore, once I import that or replace that part, I can simply, with one click, do a bunch of operations. I can mesh, I can run, all the post-processing is automatically set up based on that part. So it makes changing of the parts really efficient. So what I want to do is I want to right-click that part and say assign part to region, and then many of these parts are going to come in correctly to the region level, and now you see it populated here as the boundaries, and they all have matching names to what we defined in the part. And now if you wanted to change something up, you go up there and you change part, and that's going to populate new boundaries or different boundaries down to the region level. Okay, so yeah, we got our physics, we've got a region. The next thing to do is meshing. So onward and upward, we go to the next step in the process, which is meshing. I'm going to right-click that part, and I'm going to set up a mesh operation here with my handy pull-down menu and automated mesh, which is what I use most of the time. We're going to remesh the surface because that CAD file has very big surface mesh on it. It wouldn't work very well for CFD, and a trim cell mesher, which is one of the better options in STAR-CCM along with the polyhedral mesh. Happens to be a little faster. We're just going to set a couple of parameters around that mesh file, that meshing operation. First of all, we're going to set the base size to be 4 inches. And I sort of messed around with some of the settings earlier to figure out what works. We're going to leave everything else alone, I think. And then we simply right-click and execute. You could execute the surface mesher by itself, but we'll just do both surface and volume mesh. And that's going to take just a minute. So we'll digress while we're waiting for that to finish its operation and tell you a little bit more about that box fan filter combination that I mentioned. It's sometimes called the Corsi air box or the Comparetto cube, depending on which of the inventor you're giving credit to and which of the people who made slight changes to it. But this is the general way to put those together. I use MERV 12 for our air filters because I think that provides plenty of filtration of most of the dust and saliva and whatever else is floating around in the air. Like I said, 4 of those in a box fan. You put those around the side. You don't really have to have this cardboard that's shown here to seal up at the floor. You can really trust that the floor will provide the seal if you're on a hard flooring surface, a smooth flooring surface. And then the fan at the top, and you just seal around with all the duct tape around all the seams. Some people put this shroud on the top of the fan to keep air from coming in around the fan and up. I don't really see a whole lot of purpose in that. Yeah, it takes away a little bit of the airflow, but if you're crunched for time and you don't want to cut out a bunch of cardboard shrouds, I wouldn't say it was worth worrying about. And then here we have our fan sitting in our school's gymnasium ready to be picked up by the teachers. So pretty cool stuff. We ended up recommending 2 per room, but 1 would be better than nothing, and any of these is better than what you find off the shelf. This is taking a little bit longer than I anticipated, and that is because I forgot to choose parallel when we were meshing, but still should finish up in the next few seconds. While we're still waiting, let's talk about what are the next steps. The next thing to do is to set up some of your post-process attributes. So you're going to set up some scenes that will allow you to visualize the result as it's running, as the simulation is running, and see how it's developing. You're going to look at you're going to set up some quantities of interest. For instance, you might put a report for the total average concentration of this pollutant that we're going to populate into the room. Or you might set something around average concentrations at different elevations corresponding to where people are in the room. And it looks like we're done. So the next thing to do is to set up some visualizations and some reports. Let's go here to reports and right click, new report, and then let's just take an average value. Let's see, user overset metrics, volume average. So this will be an average quantity. What quantity do we want to take the average of? Oh, that reminds me, we forgot to set up what will be the pollutant. So we're going to go back over to our physics models and right click and change, add one physics model, which was passive scalar. A passive scalar is like having ink in a physical model. It's just something, a property that's convected and diffused and carried with the gas flow in the room. So if we wanted to study this as the filter as a way to remove a pollutant, we might populate the entire room's volume with a value of 1 of this scalar quantity and watch the reduction if we assume that the filters have 100% removal efficiency on that. Okay, once you've got the passive scalar defined, you do have to name a passive scalar. So you have to go in here and say new passive scalar, and we could give it a name. We could call it virus or dust or whatever you wanted to call it, but we're just going to leave it called passive scalar. And now in initial conditions in the room, you probably want to say that we start out initial condition, the entire room is filled with this passive scalar. And that's all. You could also define your initial condition for velocity and pressure and so on, but we don't really need to do that here, need to do anything fancy for this case. So that's it on the physics setups. Now back to my report. Volume average, I'm going to tell it to use the passive scalar, report the passive scalar. And now I want to set up both a monitor and a plot. A monitor is going to monitor the evolution of that report over time or iterations, and the plot is exactly what you would think it would be. So it automatically opened that plot. How about some visualization? So here we have the geometry. Let's make it transparent. Let's add a plane section through here. So we go to Derived Part folder and Plane Section, and this is where Derived Parts are where you're going to do a lot of cool stuff. So streamlines and thresholds and resampled volumes and isosurfaces and probes, they're all in this derived part folder, but keep it simple. Put a plane right through the middle of the filter, which sits in the middle of the room, and let's define a vector. Let's create a new vector displayer while we're at it. By doing that, we go down here to our scene, which was created when we first imported the CAD model, but you could also create scenes manually. But this one's already created. It's already got our surface in here, and now it's got a new section vector displayer. I like the option to use line integral convolution, and the defaults are to use the velocity vector field and the vector magnitude to color those vectors. So we'll see how that looks in just a second. All right, the last thing to do is to set some boundary conditions before running. We've got our fan. Let's make that a velocity inlet. And we got a couple of things to define. Let's say that the passive scalar coming on and that on that fan inlet is going to be 0 because the filter's filtered out 100% of that scalar. And let's give it a value of, say, 4 meters a second at the face of the fan. And then the filters themselves, you remember the outsides of our box are going to be the outlet of the model. So we have flow being recirculated from the fan back to the filters by definition. I think that's it. I would always recommend saving quite a bit, but we've got a 3D model, a continua defined, we have physics defined, we have boundary conditions defined, and we have a mesh. And we have some visualization, and we have some reporting. So that's the basics of a simulation right there. So we hit the running man, and things should start going here. So you see I see a vector plot in there, but it's actually grayed out. It's kind of transparent because I set the whole scene to transparent up here. So let's stop the run, and let's turn just our surface to transparent by changing the opacity of that so we can see through the outside, but the vector is not transparent anymore. And we'll click run again, and now we're seeing that vector displayer update. One thing we should look at is this was an unsteady simulation. What's the time step? Didn't even look at that, but the default when we do an unsteady is 0.001. I could probably increase that to 0.01 without much effect on stability. And then we can add the time to our displayer. By adding an annotation. Probably not a critical step for anyone, but I think it's kind of cool to see the time in the displayer. All right, so one thing you might want to do is look at, instead of coloring this vector field by the velocity magnitude, let's color it by, say, the scalar concentration in the room. So we'll choose scalar field, and then note that the color field is going to be based upon that color by that passive scalar that we set up. Okay, so you see everything's red, just starting for that filtering to happen. Just having this room air come back in and around the filters. Okay, so let's run again. And another thing is there's inner time steps here, so you'll have, like, I think the default is 5 iterations, sub-iterations inside of each time step, so it's going to take a little bit longer than a steady state simulation would take, but you see the result there already starting to happen. Blue clean air coming out of our filter. Let's look at our report that we set up. Well, now that's not working. We've got a report that's reporting 0 scalar, and so this is the interactive activity that I like to have in STAR-CCM with one user interface, everything here. You're going to not set up everything correctly, and this kind of interactivity allows you to make changes on the fly. So I think I probably already know what's happening here in this report that we set up. I didn't put a part in there. So we're going to give it our whole area here. And then rerun. And as soon as it gets to the next time step, I think we'll see that jump up to 1. Yep, there it is. So over time, that would hopefully come down. You can measure how quickly it comes down, and that way you can gauge potentially the different designs of the cube or different locations within classrooms, on and on and on. I hope you found this useful, guys. This is the kind of thing you can expect in our 90-day training, along with slide decks that walk you through important concepts outside of STAR-CCM. And really, I hope it gives you the comfort that you can do this. And with our help, I'm sure that within 90 days, you're going to be doing simulations that people that may have been working on their own to learn might still not be doing after a year or two. So until next time, take care, everybody. Bye-bye.